Okay, in this video I'll be covering several conversions. So we're going to start with formula mass, then we're going to talk about molar mass. We'll convert atoms to grams or mass, and then we'll talk about molecular formulas and empirical formulas. So first is formula mass. Here we have copper 2 chloride, copper Cu. It's a 2+ charge given by this 2 here. Chloride is Cl, that's a -1 charge. You can check that from the periodic table. If you cross, you will get Cu1, Cl2. So when you're finding the formula mass, you're just finding the mass of this compound here. And whenever you're dealing with formula mass, it's always atoms. It's always what's the atoms that you're dealing with. So since we have one atom of Cu, and you want to go to the mass, well, for every one atom, copper, if you check the periodic table, has a mass of 63.55. And since we're dealing with formula mass, the unit we use AMU. And that's just, 1 times 63.55 divided by 1, that's just 63.55 AMU. Next, we got chloride. We got 2 atoms of chlorine. Now, for every 1 atom of chlorine, it has an AMU. You check the periodic table of 35.45. Since that's times 2, you get about 70. All right. To be exact, let me plug this in to a calculator. That's actually 70.9. And that's AMU. The very last thing you do to find the total formula mass is add these two numbers. So plus 63.55 plus 70.9. So your total formula mass for copper 2 chloride is 134.45 AMU. That's your answer. All right, next, let's talk about moles, converting moles to mass. All right, this question says, what is the total mass in grams of 0.75 moles of SO2? So let's start with the moles, 0.75 moles of SO2. And we're going to mass. So we're converting, again, moles to mass. Our unknown, the unknown always goes on top. Your unknown quantity is always on top. So mass is always in grams, or grams per mole, for every 1 mole. And this is moles of SO2. So the question is, what do you plug in here? Well, what you plug in here is the mass of this guy here, SO2. You need how many grams of SO2 are there for every 1 mole of SO2. So you got to do a little calculation there. For every one mole of sulfur, you want to multiply that. And again, we're going to find the total mole of this guy. So we got to do sulfur, and then we got to do oxygen. So right now I'm just doing sulfur. So for 1 mole of sulfur, we got 1 mole on bottom. You want to cancel moles out. And if you check the periodic table, it's 32.06 grams of sulfur. So that's just 1 times 1, or 32 times 1. That's 32 grams of sulfur. Next, we got 2 moles of oxygen. For every 1 mole of oxygen, you have 16 grams. So that's just 32. Add 32 plus 32, and you get about, or no, you get 64.06 grams. That's the number we're going to plug in up here. 64.06 grams. Because that is the mass of SO2. That's the whole mass of SO2. So multiplying moles, 0.75 times 64.06, we get 48.5 0, rounded up, 5. And now that is in grams of SO2, because we are canceling out moles and we're getting grams. So what is the total mass? 48.05 grams of SO2. Next. Question asks, what is the total mass? What is the total mass of 3.01 times 10 to the 23rd atoms of helium gas? All right, so in this problem, we are going from, they're asking what is the mass, and then we're given atoms. So we got to go from atoms to moles to mass. You can't just go from atoms to mass. You got to go to moles first. That's the stepping zone here. So from atoms to moles to mass. So we're given the atoms. And this is helium. And we want moles. So our unknown quantity is going on top. Well, the number, the magic number you use with atoms is Avogadro's number. That's 6.022 times 10 to the 23rd. So we're doing some division here. It's this number here times 1 divided by Avogadro's number. Now what's good about this problem is, as you can see, the 10 to the 23rd will cancel out here. So in effect, you're really just doing 3 divided by 6, just about. So this will give you about 1/2, and if you do the calculation, it gives you not even about. We'll just do it's about, or it is 4.99. And now this is in moles of helium. So now we have moles of helium. We now have to convert that to the mass of helium. And this is a pretty easy problem now, if you're familiar with converting moles to mass like the last problem. So moles of helium times, again, we want mass on top, so we'll put moles on bottom. Again, this is just helium. For the mass of helium, just check the periodic table, it's 4. So this problem just asking you, this equation just asks you 0.5 times 4, what's 1/2 of 4? Just 2. That's in grams, since we're canceling out moles. We now have grams of helium. Next, what is the percent by mass of oxygen in magnesium oxide? And let me just fix this guy here. Okay, there we go. All right, what is the percent by mass of oxygen in magnesium oxide? So first, we got to find the mass of this whole unit here, of this whole formula here, and then we got to find the mass of just the oxygen. Thankfully, there's only one. And then we're going to find the percentage there from that. So first, let's find magnesium, or let's find oxygen separately. And we'll add to magnesium. So we got just one oxygen, right? 1 mole of oxygen. So we need the mass. Cancel out mole. Oxygen's just 16. You can check the periodic table. That comes out to 16 grams of O. Magnesium, or let me write this properly here. One mole of magnesium. So again, the mass, you check the periodic table, the mass of magnesium is 24.3. That's grams. So again, this is just 24.3 grams of magnesium. To get the mass of the whole thing, you just add these two together. So 24 plus 16. 24.3 plus 16. So you can see that's 40.3 grams of, again, this is the whole thing, so MgO. Now, to get the percent by mass of oxygen, we need to do a little trick here. All right, so we want the mass of the whole thing. has a bottom number, so 40.3. And our top number is just going to be the mass of this oxygen here, 16. So we got the part of oxygen divided by the whole unit. And then you multiply that times 100 because they're asking for a percent. What you will get is 39.7%. So 39.7% of this formula here is oxygen. Okay, next problem. What is the empirical formula for a sample of a compound that contains 259.2 grams of fluorine and 40.8 grams of carbon? Okay, usually when you're dealing with finding empirical formulas, you're given some type of percentages. But all you do with those percentages is turn them into grams anyway. So in this case, they just gave us grams. So once you get your grams, and here they're given, you just want to convert it to moles. And oftentimes, if you're doing chemistry problems, that's what you want to do anyway. If you're given grams, you got to convert to moles anyway. So let's just do that. So we got 259.2 grams of fluorine. So we want to go to moles, so let's put moles on top. Again, unknown goes on top. Fluorine has a mass of about 19. Now if you do this division, you get 13.64. That's moles of fluorine. All right, that makes sense, because that's a lot of fluorine we started with there anyway. So now we're going to do carbon. So if we got 40.8 grams of carbon, again, we're going to moles, so moles go on top. Carbon's just 12. You work out that, and you get 3.4 moles of carbon. So the trick with empirical formulas is the ratios. They're just simple ratios. So if you know, what we now have here is we've converted from grams to moles. And what we now know at this point is that for every 3.4 moles of carbon in whatever this empirical formula is, and for every 3.4 moles of carbon, we have 13.64 moles of fluorine. So our goal now is, how do we make this even more simple? The easiest way to do that is divide by the smallest number between the two. In this case, it's 3.4, and that'll just give you 1, right? And 3.4, and that gives you about 4. And what we're saying here is now, for every 1 mole of carbon, you have 4 moles of fluorine. That's what we're now saying. So you can deduce that your empirical formula is C, 1C, F, 4. Because we have 4 moles of fluorine for every 1 mole of carbon. So that's the empirical formula. All right, the last problem in this video. The empirical formula for a compound is C2H5, and its formula mass is 58 AMU. What is the molecular formula? All right, so when calculating molecular formulas, there's one thing you want to keep in mind, and that's this equation. That's on top, we're going to find X, and I'll show you what to do with X in a minute. And with this equation, it's the molar or the molecular formula mass at the top with the empirical formula mass on the bottom. And that'll give you this X value that, again, I'll show you what to do with it. So in this case, our molecular formula mass we can use this value right here as our molecular formula mass. Because they're telling us that we have a compound and its mass is 58 AMU. So we have this number. This number we're good, check. But now we got to find the empirical formula mass. Well, honestly, the empirical formula mass is just the mass of the empirical formula. That's a pretty easy thing to remember. It's just the mass of that empirical formula right there. So this empirical formula has 2 moles of carbon and 5 moles of hydrogen. So how do we get the mass? Well, we just convert those moles to grams and add them up. So we want grams. We want to cancel out moles. Carbon has a mass of 12. So 2 times 12 is just 24. Hydrogen has a mass of 1.01 for 1 mole. That's just 5.05 grams of hydrogen. If we add those two up, you get 29.05 grams of C2H5. So we now have the empirical formula, mass. Okay, so let's plug those in there. So empirical formula mass goes on the bottom, molecular formula mass goes on top. Let me rewrite this. So 58 and 29.05. Now the trick here is that we gotta derive this x value, and as you can see, it's about 2. It's 1.99, and we'll just go with 2 for that. You can always round up when you're defining these x values. Okay, so the question now is, what do we do with that x value? Well, the x value gives you the number you can multiply by the empirical formula to give you your molecular formula. Because empirical formulas are just simple ratios. Again, they're just really, really simplified ratios of the molecular formula. So what we can now do is we can take, okay, C2H5 is the empirical formula they gave us, and we just calculate this x has 2. So we're going to multiply this C2H5 by 2. What that will give you is 2 times 2 is just 4. 2 times 5 is 10. This is your molecular formula right there.